I recently had several viewers asking questions about how to combine IoTT Arduino shields like the DCC AUX Shield or the RedHat Shield with the new X8874 Motorshield. The background to this is that the X8874 is using a rather unconventional approach to using the V-in power rail, which indeed can cause problems when adding other shields to the stack. In this video I am looking into the available Arduino power options and how to best apply them to the typical use cases of a DCC-EX Arduino stack. Welcome to the IoTT channel, I am Hans Tanner. Welcome to all first-time visitors and new viewers, and welcome back to everyone else. I am happy you made it here and thank you for your support of my channel. And if you're not yet a subscriber, please click the subscribe button below and hit the bell icon so that you are always in a premium seat when new videos come out. The first topic to look at is the available power options for an Arduino. There is an excellent paper in the Arduino repository that describes that in detail. The link to the document is in the description of this video. There are 5 different ways to power an Arduino, but there are only a few boards that actually implement the battery option. So here I just look into the options that are available on most boards: USB port, barrel connector, V-in and 5V pin. Let's have a closer look and understand the characteristics and differences of each method. Here is a block diagram of an Arduino board simplified to just focusing on the power supply side. The microcontroller and other chips are just shown as 5V users, as they are not important for what we are looking at here. The first option is powering the Arduino via USB port. If we do that, 5V is delivered from the USB port to the output of the onboard LDO and to the 5V rail of the Arduino board. The current is limited to what the USB port can deliver, and we should be careful not to overload it. USB 2.0 defines the maximum current as 500 mA. USB 3 devices should be capable to deliver 900 mA. What most people are not aware of is that current can flow to the input side of the LDO via an internal clamping diode. So when connected to USB, we can measure around 4.3 volts on the input side of the LDO and hence on V-in. And it can deliver current as well, but if the current is too high, it will destroy the diode and therefore the LDO. So we should be careful about what is connected to V-in when the Arduino is powered via USB port only. For a standalone Arduino board, this is not a problem as there are no V-in consumers except one 47 microfarad capacitor. The second option is powering using the barrel connector. Important to know that the positive pole is on the center pin of the connector. From there it goes through a diode for reverse polarity protection, then to the LDO and to the V-in rail. The LDO creates the 5V voltage and feeds it to the onboard 5V users, so the microcontroller and other logic gates, and the 5V rail. Also important to know is that any voltage on V-in higher than about 4 volts disconnects the USB power line to protect the connected PC. So should there ever be an overvoltage on the 5V rail, the USB connected device is protected as long as V-in is higher than about 4 volts, which is usually the case when the board is powered via barrel jack or V-in pin. The main weakness of this mode is the LDO itself. It is a nominal 1 amp type, which is more than enough for the roughly 50 milliamps the Arduino board is consuming, but it may become a limitation if other consumers are drawing current from the 5V rail. The main problem though is supply voltage. The LDO is reducing the voltage by burning power, and the generated heat is proportional to the voltage reduction. So the lower the supply voltage, the better. According to the specification, 7 to 12 volts should be okay. Above that, or if additional 5 volt consumers are connected, the LDO is at risk. The LDO is certainly a weakness of the Arduino boards, and smoking the LDO is probably the most popular way to kill an Arduino. Other than the LDO, the V-in voltage level is safe up to 20 volts, which is the input limitation of the LDO. 20 volts actually used to be the official specification up to some time ago, and if you do an internet research, you will still find numerous references to the 20 volt value. The value was later reduced to 12 volts, and I would assume it was mainly because of the many burnt LDOs. The third method is powering the Arduino via V-in. This is identical to using the barrel connector, except that there is no reverse polarity protection. So we need to make sure that V-in is guaranteed to be a positive voltage higher than 5 volts when using V-in. The final method is powering the 5 volt pin directly. The document says it is not recommended, but then it also says that it is safe to do as long as V-in is higher than the voltage applied to the 5 volt rail. The reason for this requirement again is the LDO. If we power the 5 volt rail from external, the protection diode of the LDO is backfeeding to the LDO input, which at the same time is the V-in rail. If the current is too high, the diode and hence the LDO is damaged. So to do it safely, V-in must be higher than the voltage on the 5 volt rail, and that voltage on the other hand should be just a notch higher than the LDO output voltage so that no current is flowing through the LDO. If this is the case, it is safe to go up to a maximum of about 20 volts on V-in and power for the Arduino provided via the 5 volt rail. So these are the basic options. Now let's look into the first use case to understand how this works in an entire Arduino DCC-EX stack. The first use case is what probably most DCC-EX users are familiar with. A standard Motorshield stacked on top of an Arduino. This makes for a basic command station with 2 DCC outputs. Not a lot of track power though, but good enough for 2 or 3 HO locomotives per channel, and one of the channels can alternatively be used as service mode programming track. The simplest way to power the stack is to connect a DC power supply to the DC jack of the Arduino, as it is reverse polarity protected. And it powers the Arduino and via the V-in rail the Motorshield at the same time. There is only one problem, and that is that most model railroaders probably prefer a track voltage of 14 or 16 volts, and as we have seen, that is too much for the LDO. It will overheat and possibly let go of some smoke. The standard solution to that problem is using separate power supplies for the Arduino and the Motorshield board, not more than 9 volts for the Arduino, and whatever track voltage you want for the Motorshield. And of course, to make it work, you have to interrupt the V-in rail so that the 2 voltages are kept separate. A common solution is to simply bend out the V-in pin of the Motorshield, or even to cut it away. Personally, I don't like this solution as it constitutes a permanent and not necessarily easy to undo modification of the shield. The more elegant way is to cut the V-in trace on the Motorshield board at the location that is intended for that purpose. Yes, it is also a permanent modification, but it is easy to undo with a drop of solder, which will close the gap again if needed. My favorite way of doing the modification is cutting the trace and then soldering a diode over it that allows for letting voltage pass from the V-in rail to the Motorshield, but not in the other direction. This allows me for using a single power supply connected to the Arduino barrel connector as long as I can go with low voltage, for example for testing. And if I need real track power, I can always connect a second power supply to the Motorshield board. But to be clear, all of these solutions are just band-aids and do not fix the problem at the core, which is the too big LDO. And they come with the hassle of having to use two separate power supplies with different voltages, modifications to standard boards, and all kinds of possible sources for errors. Very understandable that modular railroaders who do not have an electronics or at least technical background may hesitate doing these modifications, and what we really are looking for is a plug-and-play solution that is reliable and allows for using just one single power supply. And that is the promise of the X8874 Motorshield, besides some increased amounts of drag power, of course. So let's swap the standard Motorshield with the X8874 and have a look at how power distribution is changing. A key element of the X8874 is the onboard DC-DC converter. A DC-DC converter has the same function like an LDO, so to reduce the voltage from a higher to a lower level. But the nice thing is that it can do it without generating a lot of heat. So we can use a DC power supply to feed the desired drag voltage into the barrel connector of the X8874. From there it passes through a reverse voltage protection. This actually is optional. It can be bridged if you want. From there it goes to the H bridges for the drag signal and to the DC-DC converter, which reduces the voltage to 7.2 volts and feeds it to the V-in rail. V-in brings it to the Arduino board and there to the LDO, which further reduces the voltage to 5 volts and feeds it back to the 5 volt rail. The 5 volt rail goes back up to the X8874 for the 5 volt users, mainly the logic gates to control the DCC signal and bring it to the H bridges. The copper trace from the DC-DC converter to the V-in rail is prepared to be cut, similar to what we have seen on the standard Motorshield, so that the X8874 can be disconnected from the V-in rail. There is no diode in that path though, so if the V-in rail happens to have a higher voltage than the input voltage to the DC-DC converter, for whatever reason, there might be some current flowing into the DC-DC converter, which might be harmful. However, in the setup as shown here, this never will be the case, but we have to remember that the DC power supply must be connected to the Motorshield and not to the Arduino. Connecting drag power to the Arduino instead would result in a high voltage to the LDO and potentially burn it, and it could also damage the DC-DC converter of the X8874. It might be best to put a piece of tape over the Arduino barrel connector in order to avoid plugging a power supply into it, following old habits. Another limitation to keep in mind is that the 5 volt power is still limited to 1 amp maximum, as it is generated by the Arduino onboard LDO. This is not a problem in the setup as shown here, but it may become a limitation once you add other 5 volt consumers like LEDs or servo motors. The 1 amp ceiling is reached faster than we think, and it is a peak value and not what is available on an ongoing basis. The second way to achieve the goal of only having a single power supply for the entire stack is using a DCC AUX Shield on top of the standard Motorshield. Like the X8874, the DCC AUX Shield is using a DC-DC converter to bring down drag voltages of up to 18 volts to the 5 volt level suitable for the Arduino and other 5 volt consumers, and up to 3 amps of current are made available on the 5 volt rail. It receives the input voltage either from the barrel connector with reverse polarity protection or from the V-in rail. If power is received through the barrel connector, the board puts it to the V-in rail as well, so it is available to the other shields in the stack. On the next lower level in the graphic, the Motorshield, V-in is used to power the H bridges with the drag voltage, and 5 volt is used for the gate logic to control the DCC output, just as before. On the Arduino level, Vin is applied to the LDO, and as we have seen before, Vin will also switch off the 5V power supply to the USB port, so that any computer 5V line is disconnected from whatever comes in via the 5V rail. The LDO output is set to 5V, but since this is countered by the 5.1V received from the DCC AUX Shield via 5V rail, no current is flowing and the LDO stays cool. And as long as the input to the LDO remains at Vin level, no reverse current can flow through the LDO either. In other words, the Arduino onboard LDO is completely bypassed. And as we can see in this setting, the track power from the power supply can be applied wherever it is desired. We can use the barrel connectors of the Arduino or the DCC AUX Shield, or we can supply DC power to the terminal block of the Motorshield. In each case, the input goes to Vin and the DCC AUX Shield, where the 5V is generated and supplied to the 5V rail, and from there it goes to all the 5V users of the stack. The best place to connect the DC supply is the DCC AUX Shield, as it has reverse polarity protection and the shortest distance to the DC-DC converter. Feeding the stack via Arduino barrel connector results in a slight voltage drop along the Vin rail, and feeding via terminal connector of the Motorshield bypasses the reverse polarity protection. If we hook up the oscilloscope to the Vin and 5V rails, this is what we get when DC power is connected. Vin goes up and the 5V rail goes to 5V from the onboard LDO. After about 10 milliseconds, the DC-DC converter is powered up and the 5V rail voltage increases to about 5.1V and the Arduino LDO is bypassed. So much for the basics about using a DC-DC converter to generate the voltage on the 5V rail. This table shows the key differences and how I evaluate them within the context of the simple use case of just one Arduino and one Motorshield. Both solutions solve the basic problem of the overheating Arduino LDO while still allowing for using a single power supply to supply track and the Arduino stack. The main difference is that the DCC AUX Shield puts the track voltage right to the Vin rail of the stack with sufficient current so it can be picked up by a Motorshield or other consumers requiring track voltage, for example a second Motorshield. The X8874 on the other hand puts 7.2V to the Vin rail to feed the Arduino LDO. There is really no other use for this voltage, which basically means that the Vin rail is no longer available to power other shields on the stack. That, in my opinion, is the main disadvantage of the concept, as we will see if the use cases get a little more complex. The other difference is the available 5V power. The X8874 still uses the Arduino onboard LDO with a peak current of 1 amp and a more realistic continuous flow of maybe 500 milliamps. The DCC AUX Shield makes 3 amps available on the 5V rail, which is beneficial if you want to power additional consumers like an LED chain, which draws maybe 50 milliamps per illuminated LED, or if you connect servo motors for turnouts, semaphore signals and the like. One advantage of the X8874 I see is pin safety of the Vin connection between the boards. If Vin gets disconnected, all that happens is that the Arduino stack is no longer powered. The same is the case if the 5V rail gets disconnected. It just removes 5V power from the other boards. With the DCC AUX Shield, the risk is higher. If the 5V rail gets disconnected, the LDO is exposed to the track voltage and generates the 5V for the Arduino board. Since the current is low, typically around 50 milliamps, it will not go up in fumes immediately, but it might heat up significantly, depending on the track voltage. If Vin is disconnected, the LDO input gets reverse voltage from the 5V rail, but since there are no consumers for Vin on the Arduino board, there should be no harm, and the roughly 4.4 volts seen on Vin in that case should still be good enough to turn off the USB power supply. So the damage potential is limited, but still some care should be taken to ensure good connection between the different shields of the stack. Bad contacts are caused by pins not properly inserted in the receptacle or boards that are twisted or bounced so that the pin does not properly fit in the header of the lower board. Another possibility is that the boards are just inserted all the way in, and solder joints of the upper board may make contact to pin headers of the lower board. In general, these problems can be addressed by using proper spacing between the shields and correct alignment of the shields in reference to each other. That's why I usually recommend using the 3D printed IoTT Cube shield frames. They ensure proper spacing between the shields and also help with the correct alignment of the shields when assembling the stack. The good news is that I now have added a frame for the x8874 as well. It is currently being verified and will soon be released to the public section of the Tinkercad repository listed in the description below. Now let's look into a slightly more complex use case, and that is combining the x8874 Motorshield with the DCC AUX board. Why would someone want to do that if the x8874 already has a DC-DC converter that solves the LDO problem? Well, because of the additional functionality of the DCC AUX Shield, which has a connector for the IoTT stick and an output for a NeoPixel string. Adding the IoTT stick to the DCC AUX Shield makes the DCC-EX stack a wireless Loconet command station and adds features like Wi-Fi connection to JMRI, a Vice throttle server and an MQTT gateway to the picture. The NeoPixel string allows for controlling individual LEDs using turnout and signal commands or information from block detectors and more, so it becomes quite easy to make a local CTC panel directly connected to the command station. So how does it look like if we want to use the DCC AUX Shield in combination with the x8874 from a power supply point of view? Here we go. The easiest way is to power the x8874 with track power. As we have seen, this puts 7.2 volts to the Vin rail and creates 5 volts on the 5 volt rail via the Arduino onboard LDO. The DCC AUX Shield receives the 7.2 volts from Vin and activates the DC-DC converter, which puts 5.1 volts on the 5 volt rail and bypasses the onboard LDO. So the 5 volt rail current is now increased to the 2 amps available from the x8874 DC-DC converter. The IoTT stick consumes about 100 milliamps in average, which can go up to about 250 milliamps when the internal battery is recharging. This should leave about 1 amp for other 5 volt consumers like the LED chain, which should be sufficient for most applications. Also in this use case, make sure you only power the stack via barrel connector on the x8874 Shield. Using any other connector to supply DC power may cause harm to individual shields and should be avoided. It might be best to block off the connectors that shouldn't be used in order to avoid unintended plugins. If you need more power on the 5 volt rail, you can connect an additional DC input to the DCC AUX Shield so you can get up to 3 amps of 5 volt power. If you do that, the DCC AUX Shield will output whatever voltage you supply to the Vin rail of the stack, which causes a conflict with the 7.2 volt output of the x8874 Shield and can cause harm to the DC-DC converter. To be safe, you need to cut the Vin trace on the x8874 board so that the 7.2 volt output is disconnected from the Vin rail. Optionally, you can also cut the DC-DC converter enabler link so that the 7.2 volt output does not even get generated and a few additional milliamps may be conserved. You still have to cut the Vin trace in that case though. The final use case to look at in this video is adding a RedHat Shield to the stack. The RedHat Shield adds wired loconet capability to the DCC-EX stack. So if you want to switch over from a loconet command station to start using DCC-EX, but you have a ton of peripheral devices like handheld throttles, turnout decoders with loconet feedback, block detectors and so on, the RedHat Shield allows you to use these devices with the DCC-EX command station, as it provides one loconet B and two loconet T outlets. These outlets need to be powered from a supply of 12 to 16 volts, which is expected to be received from the V-in rail. In the standard setup using the standard Motorshield or IoTT PowerShields, this is no problem, as the V-in rail carries track voltage, which is then limited to 16 volts and used to supply loconet. When using the X8874, we run into the problem that the V-in rail is already blocked by the 7.2 volt output of the X8874 shield, but 7.2 volt is nowhere close to the voltage that is needed to supply loconet, which asks for a minimum of 12 volts with an upper limit of 24 volts. In order to power throttles on the loconet T outlets, the voltage also needs to be north of 12 volts, as is the case with the rail-sync signals on the loconet B outlet, which can be used to drive additional boosters. So we need to have track power on the V-in rail in order to generate the 12 to 16 volts on the loconet outlets, which means we need to supply the DCC AUX Shield and cut the V-in trace of the X8874 Shield as seen before. The X8874 Shield gets the 5 volts for the logic chips from the 5 volt rail, but must be connected to an additional power supply that provides the track voltage, so we end up with a 12 to 16 volt power supply connected to the DCC AUX Shield and the track voltage power supply connected to the Motorshield, and the DC-DC converter output of the Motorshield must be disconnected from the V-in rail. And that's it for the use cases I wanted to cover in this video. I hope this was useful or at least interesting for you, and you have a better understanding of the various power options available. The X8874 Motorshield is a pretty new device, and I expect additional questions to come up as more people start using it, so I may cover additional use cases in future videos. If you have specific questions, please use the comment section of the video to bring them to everybody's attention. And if you like this video and the topics covered today, please click the like button below. Doing so supports the IoTT channel and helps to promote this video to other model railroaders because YouTube likes the likes. Thanks for watching and see you in the next video.